Welcome to Chemistry Lab. Today's lab, buffers and salt solutions. Buffers, well, buffers are pretty much what you think they are. They resist changes in pH. What we're going to do today is calibrate a pH probe. You've done that before. You do it again with your pH 4 and pH 7 solutions. And then we're just going to measure pH of different solutions. You're going to start out with just water. And we know that plain pure water with nothing dissolved in it should have a pH of 7. But water that's in air actually has a slightly acidic pH. And let's think about that here at first. Carbon dioxide from the air can dissolve in water, especially when you're stirring the water. You're essentially stirring air into the water, and you can generate a little bit of bicarbonate ion and hydrogen ion, thus making the solution slightly acidic. So when you set up everything at the beginning, you're probably going to see a slightly acidic pH. Don't get too concerned about your pH value matching your neighbor's. The calibration process has quite a bit of air in it, or it can at least. So what's important in this lab is to compare your pH readings with other pH readings that you're gathering rather than your neighbor's. But you should see something just a little bit acidic because of this. Then once you've measured the initial pH, you're going to add a little bit of strong acid to the water. And of course, you ought to see an acidic pH. Then you're going to add some strong base to it. And of course, you ought to see the pH go in the other direction. In part 2 of the lab, you are going to look at acetic acid, which is a weak acid. And you should see an acidic solution when you just have acetic acid and water. But you'll add a buffering salt to it. And once you have your buffer system set up, you'll add some strong acid and strong base to it. And you should be able to compare the effect of a buffer system to what you saw in the non-buffered water that you had done in part 1. In part 3, you're looking at pH of different strong acid, strong base solutions, weak acid, weak base solutions. You're making a lot of solutions in this lab. Some of these solutions will need to be diluted down from more concentrated solutions, and you can use your dilution equation to determine that. Some of these solutions will be needed to be made from solids. You'll have to figure out how much solid you need to weigh out in order to make that solution. So you get a lot of practice with that in this lab. It's good review here at the end of the semester. In part 4, you're looking at pH of salt solutions. And just to remind you, if you have a salt solution, for example, something like iron chloride is soluble in water because all chlorides are soluble in water except for silver, lead, and mercury. So in water, we get iron ions and chloride ions, right, dissolving in aqueous solution. And when we think about what the pH of a salt solution ought to be, we look at how each of the ions would react in water. Right? If we think of iron ions reacting with water, I'm going to write water as H plus and OH minus together, so we can think of the positive ions picking up the negative ones to generate, in this case, iron 3 hydroxide with 3 hydrogen ions left over. Right? I need a 3 here. There we go, balanced. And iron hydroxide, this is not a strong base, and so that means that some of this is going to stick together, and every time we get an iron hydroxide unit that forms, we're generating 3 hydrogen ions, right? That would make a solution acidic. Think about what would happen here with chloride ion in water. Right? Chloride ion is negative. It would pick up the hydrogen ion, HCl plus OH minus, except that hydrochloric acid is a strong acid, and strong acids ionize 100%, meaning that none of the HCl is going to stick together. This doesn't happen, right? Chloride ions and ions of strong acids do not react with water. Therefore, It's the first reaction that is determining the pH, and every time we get some, because iron 3 hydroxide is not a strong base, so every time this sticks together, we're generating hydrogen ions. So if you have the anion of a strong acid and not the cation of a strong base, we're going to have an acidic solution, right? Anion of strong acid generates an acidic solution. If you have the cation of a strong base, we're going to have a basic solution for similar reasons. If we have both, it should be pH neutral. But that's what you're doing in part 4. You're preparing different salt solutions and measuring the pH, and it should at least fall where you predict that it would. In part 5, you're looking at pH changes in buffers again. And let me just look at an example here, because you're writing a lot of reactions and then looking at shifting equilibria in order to answer questions in the lab. For example, let's look at the acetic acid acetate buffer system. Right? Acetic acid in water. We get some hydronium ion and acetate ion. That's a 3. Yeah. Remember that a buffer contains a weak acid with a significant amount of its conjugate base. So in an acetic acid buffer system, we're talking about acetic acid with a significant amount of acetate ion, often coming from something like sodium acetate or potassium acetate, some soluble acetate salt. Right? So the weak acid component is giving you some hydrogen ion. Its conjugate base is generating some hydroxide ion. So a buffer system means that these two things are happening together in the same pot. So if you take a buffer system and add some strong acid to it, what we're doing is increasing the amount of hydronium ion when we add a strong acid to it. Now, we know from Le Chatelier's principles that if we increase the concentration of anything in a system at equilibrium, the system shifts so as to offset the equilibrium. This first reaction, therefore, shifts to the left when we add strong acid to it. Think about what happens to this second reaction. When we add strong acid to it, the strong acid will react with the hydroxide ion to make water. And what we're doing is decreasing the concentration of hydroxide ion, and the system shifts to make more of what you just took out. So this reaction should shift to the right whenever we add a strong acid to the system. Both of those things happen at the same time. The end result is that you have neutralized the acid that you've added. That's why you don't get a strong pH change or a large pH change when you add a strong acid to a buffer system. Now, the reverse occurs if you add a strong base, right? This bottom reaction will shift back to the left because you're increasing base. So this system shifts to the left. The base will react with the hydronium ion, causing this to decrease. So the top reaction shifts to the right. And that's what you're doing in this part of the lab, is you're writing these equations for different buffer systems and describing how these systems should shift when you add strong acid or strong base. There are several questions at the end of the lab. One of the more interesting ones involves lead ions in solution. And the question has something to do about the effect of pH on lead ions that are dissolved in water. And if we look at a reaction of lead ions in water, lead is positively charged. It would pick up the lead ion, the hydroxide ions and negatively charged parts, and give us 2 hydrogen ions left over. Lead hydroxide, that's not a soluble compound, right? That forms a solid. The hydrogen ions are in solution, right? So if we think about this in terms of drinking water, right? We know that lead ions in drinking water, that's a terrible thing. Lead in small concentrations can have serious physiological effects. But if you have lead ions in water, yes, some of that's going to get tied up in lead hydroxide. And when that happens, you've got a solid, and this solid will often stay on the inside of your pipes, right? You get a crusty layer inside water pipes, and that crusty layer can include this compound if lead is present. Now, the good thing about that is this keeps lead out of your water, right? Because it's a solid. So if it stays as a crust and it doesn't get in the drinking water itself, I mean, this is the bad stuff, because this is dissolved in water, and this is going to be the stuff that you could ingest. This would be much better. Now, if this system is set up, think about the effect of pH, because we've got hydrogen ions here. If we increase the pH, well, let me say, instead of increasing the pH, let's talk about increasing hydrogen ions, which would decrease the pH, right? If we're in acidic solution, then what would happen is we're increasing the concentration of H+, causing this reaction to shift back in this direction. That would be a bad thing, because we would get more lead ions in water, right? And the reverse would be true if it were more basic, because the base would react with the hydrogen ion, cause this to decrease, and this reaction would shift in this direction. That would be better, because it would take more lead out of solution and put it in the solid. This dynamic that we're describing here is similar to what was happening in Flint, Michigan, when they shifted water supply. The water supply they started using was more acidic, and the lead that had been tied up in these pipes, right, the crust in the pipe, began to dissolve, right? More acid meant that this reaction shifted back in this direction, and we got more lead ions in solution. It's interesting now that we can explain the dynamic of real chemistry using some of the things that we've talked about in the class. I believe that's everything. Have a great lab.